we have Oscar Koller, Dr. Oscar Koller. He's working at Microsoft as a principal applied scientist. And let's give him a big applause.
Yeah, thanks for having me here. I'm really excited to be here. It's been a great venue so far, and it's so energetic. It gives me really like a very good vibe to see so many people, some of whom I know already since many years, and others I don't know. Yeah, I want to basically talk about our advances in sign language modeling and sign language work at Microsoft from a production point of view. It's kind of like a challenging bit to take what kind of is happening in research and actually apply it to products. I also want to point out that the work that I'm representing here is like some small aspect of what's happening at Microsoft. It's a huge team effort. I'm representing work that is done by a lot of my colleagues, and quite a few of them are deaf. So yeah, I really enjoy that kind of like the field is moving to deaf-led projects, and that's definitely also something that we are following and that we are very aware of at Microsoft. So yeah, the title of my talk is Sign Language AI at Scale, and yeah, some of you may know parts of it. There's some overlap with what I've presented at ICCV, but there's also a few new parts here. Basically, I want to start the session with how I usually introduce this work, which is like I typically ask the audience, have you ever seen a deaf person in a remote meeting? At Microsoft, we care a lot about Teams, so in a Microsoft Teams meeting. And I guess here the situation is different because there are a lot of deaf people in the audience, but often hearing people have not, and they just don't realize like what is it like to be on a meeting with deaf people. And then there are several reasons for that, right? I mean, I guess most of you here are expert in that sense. One of the reasons is like when you're on a meeting and there's a deaf person in that meeting as well, they join the meeting with their interpreter, they start signing, start maybe even giving a talk, they completely disappear from the front page, right? You either can manually pin them, I guess that's what many of you do, but if you're not even aware that there is a deaf person in that call, these people will not get any stage presence. Like instead, what my deaf colleagues have told me is that like the interpreters are being complimented and are being kind of like thanked for great speeches, great thoughts, great participation in talks, but instead it's completely kind of misled, and the actual contributions were done by the deaf person, and that very problem is something that my deaf colleagues, and we have about like 5 to 10 deaf full-time employees at Microsoft in the US that I collaborate with, came up to us and basically put up as a major problem in their use of Teams as a remote communication tool. And so that's like the majority of that talk, what this talk is about, how we build that feature, and what to pay attention to, what we did pay attention to, and what you have to pay attention to when you want to create such a maybe rather simpler feature, but still kind of difficult to make it work at scale in a real product. So I just want to make it very clear, like, I mean, obviously there are many experts here in this room, but what I'm mostly talking about is sign language detection. And I want to distinguish that from what we've heard today, like sign language recognition in the older times, sign language translation. So sign language detection really is the problem of detecting when someone signs and not what they are signing. So let me start by showing you a quick internal demonstrator when we first had kind of like an initial model up and running, and just kind of to visualize how that would actually work. So you do see here like a meeting.
Just stop explaining and then show it, because otherwise we can't see. Is that all right? Thank you.
So I'm showing it here. So I'm stopping the video, and basically what you could have seen is a meeting in Teams where you have signing participants and you have speaking hearing participants, and you do see the focus or the sign detection being represented by a blue outline around the signer's face or around the signer's webcam. And you do see that for the speakers, as this is known in meetings, and you also do see that for signers here. And that's exactly kind of like the feature that we're talking about. In this demonstration, you also saw like a small visualization of the model activations on the left side. I can replay it again, then you can pay attention to that another time. That basically shows some details of the internal model that we're going to talk about. In this demonstration, what you did not see is that actually when you have multiple people on the stage, some people are prioritized over others because not everyone fits on the first screen, on the main page. And that's actually when this feature becomes very powerful, because then you actually see who is currently signing or speaking. Let me just play kind of like the starting point of it again, and you can pay attention to the blue outline again, and to the activation of the model here on this side when here my colleague Toby is starting to sign. All right. Yeah, other kind of like follow-up possibilities this enables is like you can actually do proper attribution of the uttered content by actually displaying the name of the signer in front of the captions. So you can have automatic captions. These captions represent what the interpreter has been speaking about or has been translated, and that in the current form is kind of showing the name of the interpreter, and in the kind of released form, this is actually showing the name of the deaf person that is linked or tethered to the interpreter. And that obviously has some benefits also in the post-meeting analytics. So there is like a summary page right after each meeting that Teams can generate for you. And in my past experiences, in my past meetings with deaf people, when I want to find something that Toby, for instance, was signing about in one of our joint meetings, what I had to do is actually remember who was interpreting for Toby, and then search for that interpreter's name, and then I could find that content, and that's going to be a thing of the past. So this feature, as we're speaking about it, has been released to the public as of July this year, and it's not kind of like public in all aspects. So I think the showing the right attribution of the signer in the meeting summary is, I think, just rolling out, but the feature itself is already on the public branch of Teams, and you have access to that, and I'll show you how to activate that. So let's talk about, or let's look into some of the details of what is under the hood of this approach that we're following. So we really required this to be a very stable, very mature system to work on in the wild footage. So obviously it has to run quickly so that it kind of directly gives you information on who's signing. It has to run at a low cost. So we opted to have this actually deployed and run on the client's devices. So if I'm running Teams on my laptop, then it's actually a model that is run on my laptop locally. And at the same time, yeah, obviously it has to generalize across different individuals, across like different backgrounds, strange camera positions, strange artifacts. It's currently designed in a way that it's intended for remote participation only. So it's been applied, or it's assuming that there's one signer in the camera and not kind of a room of participants. So we've designed a two-stage system, and part of the reason is that like we have scarce data available, and we have different data sources for each of these components, and I'll talk more about this data in a second. The first stage is the landmark or feature extractor, if you want. That landmark tracker basically predicts a sequence of landmarks, 2D landmarks. Actually, in our case, we are modeling 95 2D landmarks on the body. We perform some kind of normalization to ensure that these features generalize better across individuals. And then we have a detection stage that actually takes into account the temporal sequence and models the sequence to predict the binary class label of is someone signing or is someone not signing. So in terms of architectures that we've chosen, I have to add that this system is this feature is rolled out for desktop, both for Windows and for Mac, and it's rolled out for web as well. So those are the platforms where detection works. You can receive detections and see them on any of the platforms. So also on mobile, for instance. For the desktop setup, what we opted for is like a pre-trained backbone. That here is a MobileNet v3 architecture, has 2 million parameters, and obviously it also has to be quite small in size, because a user, when they first activate the feature, have to actually download the model in the background. And so it's 7.5 megabytes in space, disk space. The sign detector is a very small one-layer unidirectional LSTM with like a limited number of parameters, 65,000, and very small in space as well. The interesting bit is that we actually leverage synthetic data to train the landmark tracker, and this basically brings us into the position of generating very diverse data that basically generalizes and where we can, by definition, make sure that it generalizes across different appearances, different ethnicities, different camera configurations, and we can basically predefine those and also like play around with them to overcome certain issues that we see on production traffic, or kind of like on traffic on test cases that we observe essentially. Right, the landmark tracker, because it's kind of having access to very diverse data and very well balanced data, can be trained on as little as 1 or 200,000 images, and it then generalizes. The actual production model is trained on the synthetic data, and then kind of like in a retraining, we also add real data pseudo-labeled on top of it that helps kind of like improving performance, but the base model really works very well just based on synthetic data. And I want to talk more about this synthetic data. At the bottom, you can see here an early state of our synthetic data pipeline. And you do see one of my former dev colleagues who was signing. And in the second window from the left, you see an early model predicting the dense landmarks on her body, and then you see in the third image a blue parametric mesh representation, which is based on our internal parametric stack, which is very similar to what was previously referred to as SimpleX. We call this SOMA, and it's been at least described publicly as well. And then in the fourth window here, you see basically a rendering of exactly that synthetic, of that reconstruction, of that fitted SOMA shape rendered in a synthetic environment. Right. I want to call out that the nice thing about this is that we get perfect ground truth, right? For this synthetic data, we basically generate it in a way that we have the identity of the person first. We do have a certain pose that we can kind of like fit the body or the shape to. We can apply a certain clothing, certain set of accessories, and then we can give it a certain texture. And we can render the whole thing in a specific environment. And this is, for each of these parts, basically we have perfect ground truth. And that ground truth is not manually annotated, but it's actually synthetically rendered and has a 100% match. So we get vertices from which we can pick the landmarks that we care about. We get a skeleton and can basically get the pose rotations, the angles of the body joints, segmentation masks, normal masks, depth masks, and albedo. So all of that is basically available for further learning the models. And this is basically it's work that some of my colleagues here in Microsoft Cambridge published last year at SIGGRAPH. It essentially has two stages, right? Like we first train the landmark tracker, a dense landmark tracker here that is based on a larger backbone here in HRNet. It has three heads, a landmark head, a pose head, and a shape head. The landmark head is what really matters for our fitting. But the poses, for instance, are used to initialize the position before fitting, basically as an initialization. The whole thing is trained. The model is trained with a negative log likelihood loss, which has the advantage that it essentially predicts the uncertainty at the same time as the 2D landmark, and this uncertainty is then used to scale the data term in the model fitting. So that has the advantage that when a specific body part is not observed or is cut off, that from a particular camera view, for instance, that we can then, or that it's then automatically down-weighted and not taken into account, or taken less into account for the fitting. We do have a few regularizers during the fitting process that correspond to shape and expression and pose, and a temporal prior that makes sure that there's less jitter in the final fit. Another loss that essentially does not, or that ensures that we do not have intersections of the body and around the camera perspective as well. We had to play around with these quite a bit. I mean, I'll talk more about that in a second. But essentially, this is the main pipeline, and obviously we need data to use it to get to these representations that we can then synthesize. And in this video, I'll just show you very quickly how our data capture efforts look like. Right. So this is Chris, one of my dev colleagues. And yeah, you see our multicam rig with time synchronized cameras, and that's basically where we are gathering the sequence data. These are examples of some of the generated synthetic images that we can gather from it, and each of those comes basically with perfect ground truth. And here you see kind of you get an idea of the variety of images that this landmark tracker is then finally trained on. Right, and now I want to kind of use this point in time just to expand a bit beyond kind of the scope of this sign detection work. We've had a recent collaboration with the TU Munich and with the Barcelona Supercomputer Center, and have currently work under review that is also leveraging this stack and trying to basically make data assets available to the research community. So we basically are in the process of releasing a refined version of How to Sign, which we call How to Sign Synth 3D, which contains 3D reconstructions of how to sign green screen. But How to Sign actually came with 2 views. I've not heard of anybody actually using the side view. Maybe I'm just not aware of that. But basically what we did was we time aligned these 2 views and reconstructed the data with that. And we're sharing basically these reconstructions. We also reconstructed a set that was previously available from How to Sign, but only on request. And I have not seen anybody actually using it. It's called the panoptic subset of How to Sign. It was captured. Amanda captured that in the Panoptic studio of CMU Labs, and it's basically a multi-view data set that covers the same signed interpreted sequences as the validation set of How to Sign green screen. And we again kind of like boiled it down to like usable cameras from that huge set and applied our algorithm to it and refined it and are releasing the 3D reconstructions of that. Well, and then we are also releasing a synthetic test set that is based on our own capture. So it's totally unrelated to How to Sign, but allows us to basically allows us and us as the research community to test kind of rendering or fitting approaches on out-of-domain data. And finally, we're releasing the synthetic train data that we use to train these landmark trackers. So what we are also kind of writing about, what we're also writing about in that paper is a fit render retrain loop, and that's kind of like very nice about this synthetic pipeline. Initially, our synthetic pipeline was not kind of created with the intent of capturing and fitting 3D sign language data. Instead, like we've focused on a variety of use cases. I mean, you can imagine like in Microsoft there are a lot of use cases around maybe other meetings but not actually sign language. And so initially we did not have any sequence libraries or any 3D reconstructed bodies of signers in that data. And so here in this paper, we're describing the gains that you can actually get when you start to include sign language data into this into training your landmark trackers. And we're proposing a loop of taking multi-view data, like here you're seeing these CMU recordings on the very left side, and then kind of using an initial version of dense landmark trackers, then doing the model fitting and generating one version of these sequence libraries that are 3D reconstructed parametric body models, and then these can be used in the final step to generate synthetic data that comes with, again, the annotations and the ground truth that we need to retrain our landmark trackers. And with this kind of like render, retrain loop, we can then iteratively increase the fidelity of our reconstruction and of our model fitting process to capture very nicely the particularities of articulated hands as they occur in sign language real footage. And you do see here some, I mean, I'm not going to talk about all the details. I guess that would be a different talk here, but you do see that kind of like starting from our initial baseline, which I term as iteration 0 here, we get up to 60% relative reduction in landmark tracking error on the hands by iterating with this sign language data, by including essentially sign language sequence data. And this sequence data is what we are making publicly available. Right, and I want to show you a visualization of this data on the how to sign panoptics set, and also of the synthetic nature of that data again. And I'm not sure if it was visible, but you do see some jitter in the beginning of the data, and that's also like why I'm very interested in how to reduce such jitter, because that's obviously annoying to look at. Okay, I want to go back to our work on sign detection, and I want to speak about quantitative testing. Like how do we actually make sure that our landmark tracker is working and is ready to be released. So essentially just looking at the evaluation metric of our landmark tracker. And I just want to understand, how much time do I have left? Okay. So so here you see an experiment on the amount of data that we actually use in training this sign language detection model, and you do see here like 100,000 images that are non-sign language related, and then we're adding like up to 100,000 images, and you do see kind of again an impressive improvement by adding sign language data, but actually actually kind of like not retraining it here for this work. On the sign language detector side, we are evaluating that in a zero-shot fashion, and that's also something that I want to really kind of suggest to be doing more in the research space in general. I think earlier talks mentioned kind of like the need to move away from like artificially old data sets that are kind of like not representing the current state of the field and the current problems that we want to tackle. And indeed, that's absolutely right. I think we should really increase our vocabularies that we test. We should use current test set, but I actually would emphasize that I would love us I would love to see the field evaluating in zero-shot fashions more and more. So literally, do not train on the train set of a particular translation data set, but actually just evaluate on the test set and train it kind of like on a variety of data sources that are more and more becoming publicly available, right? So here for the sign language detector evaluation, we basically have frame-based metrics that tell us how well the sign detection works, and we have kind of like a different like a variety of different recordings that represent certain scenarios or certain problems that we witnessed in the use of our model. We have like video conference conditions. We have like noted that when signers just use one hand for signing, that actually the sign detection isn't as reliable. So we started recording like a particular test set for that case. We noticed that the model in the earlier kind of version was quite easy to detect what we termed hard negatives as signing. So when people actually touch their face, or when they scratch, I don't know, their cheek, that actually becomes treated as signing. And so we recorded a particular test set for that case. Yeah, and yeah, obviously, kind of like it's important for us that the model works both for right hand and left hand dominant people in the same way. So we mirrored the data sets and ensured that the performance kind of is similar in both cases. We perform segment level testing, so we are actually interested that nothing, kind of no information of the signer that's being transmitted gets lost, and so obviously kind of the sequence information is very relevant, and annotated data particularly for that purpose, and looked at the missed signing segments rate, looked at the false positive segments rate, and obviously kind of we do care about the onset and offset delays that the system introduces. Well, and then finally, what matters a lot to us as well is that the system does not discriminate certain gender, ethnicities, age groups, certain sign languages, certain eyewear, background condition, video quality, and so we created test cases to measure kind of like these particular conditions and basically act upon them. Well, and then I would say that it's absolutely crucial if you want to deploy something, or even if you just do research, or even if you do research, sorry, that you actually look at outputs of your model and at your predictions. And so we have different forms of visualizing our model's predictions. We overlay, we create like time series plots where we kind of get a glimpse of the sequence behavior of the model. We annotate individual videos and kind of look through them and watch kind of like what are really the predictions here, and if something goes wrong, like try to nail it down and try to understand like what was really problematic. And that's also again the advantage of an interpretable two-stage system that you can actually go in and try to figure out like what bits and pieces you need to improve in order to make it work. Okay, finally, I want to play the demonstrator. This hit, as I said, this had hit production in July this year, and this was kind of like the first time that we tested it in the production system back in June, I think it was back then. And yeah, I'm just showing you. You can focus at the two bottom videos here, two of my colleagues signing, and you'll see again how they get highlighted. All right, this is how you can actually enable the feature in Teams. So you need to go into your settings, into accessibility, and then you self-identify as, you turn on sign language mode and you self-identify either as a signer or as an interpreter, and that's kind of how the model is. When you select I'm a signer, the model gets downloaded and gets executed on your local PC. All right, so to recap, in general, we are working on solutions that improve accessibility for deaf people across all Microsoft products. We are operating in a deaf-led fashion. We have a lot of deaf colleagues, and they lead these projects. We are aiming for collaboration. So we do want to kind of, our goal is to speed up the field, to make sure that the sign language technologies are not just solved in 2045 or 54, whatever you mentioned earlier, Rich, but that this can actually happen way before that. And we want to kind of encourage collaboration and really be open about the resources that we create and make what we can make available to the research community. Well, and finally, like I spoke a lot about synthetic data that is flexible and much easier for us to get through privacy reviews and compliance, and has shown, at least for specific use cases, to be as good as real data. We've kind of briefly talked about zero-shot evaluation and the need for it, and moving to kind of challenging test situations in general. So yeah, that's what I wanted to share today. Thanks so much for your interest, and I'm happy to take questions on this.
Thank you for the presentation. We can have two.
Can we bring the microphone over? Sorry. Yeah, we'll have to get. We only have one microphone. Sorry. Okay, try that.
Which one? Yeah.
Yeah, you have to take both.
Take both.
For the recording.
You had mentioned for the tracking that you're still concerned about the jitter, but also I think following what we were talking about earlier, is there much concern about signs that have like contact, hand on hand or hand to the face? Is that kind of already in the reconstruction pipeline, the rendering stuff you were talking about, or did that need to be addressed as well?
Yeah, that's a good question. I can just speak up. That's fine. I think I speak up. So that's a good question. So the jitter, I'm less concerned for tracking in general. I'm more concerned, like, if you want to replay it, as I've shown you, kind of like a sequence of synthetically generated sign language footage. At that point, kind of jitter really becomes not so pleasant. I think for the landmark tracking itself, jitter does not play a big role for us. For the reconstruction, obviously, yeah, it's a chicken and egg problem, particularly if we use the same data to train our models. However, we do not train these landmark trackers in a sequential, or they have no sequential information. They are per frame classifiers, and so that is part of the reason why we have jitter, probably. But that is also kind of a reason for why jitter doesn't matter in that case. And you asked about hand interactions. Hand interactions are challenging. We could solve them by our fit render loop partially. So the model works well on interacting hands, and it's kind of like a single. Well, it's not truly a single model. It's like a dedicated face model. It's an upper body model, and it's a hand model. But we do not model in particular hand interactions. And yeah, but it's definitely something to closely monitor and watch, and something we can improve upon.
Probably one more question.
Yes.
Yeah. Just the mic. Oh.
Where are the mics?
This one as well.
There you go. So I've got a couple of questions. So first of all, congratulations to the MS team. I used to work there before, but there were accessibility issues with MS Teams. Sorry, I used to use it, not work there before. And so when you were talking about the blue border as when you have sign detection, what about the other way round? So if I'm not signing, but the interpreter's voicing over for me, does the blue border detect the translation or detect me? So as I'm signing, so do you see what I mean?
Yeah, you're basically saying if the sign detection is not triggering, or if you are not signing maybe very manual signs, but you're rather maybe just nodding or making some kind of like a back channel information, like and that still leads the interpreters to interpreting. Will that still be attributed to me or not?
Yes. Yes, because sometimes the hearing people will also be touching their bodies as well, and they'll be playing with their hair, and and I just worry about the fact that I might be signing a little bit, which the interpreter's doing, but then someone else is just making manual movements which aren't sign language, and I wonder if it will kind of trigger a false positive.
Yeah.
And sorry, also just to say the main issue there is as well, when you record Teams, for example, for a demo or a screen share, when you look back at the video, it always shows the interpreter for voiceover, but not the person who's signing. And that's always an issue with sharing screens. Is that something that's addressed? I wonder if you've already resolved that issue.
Yeah. So there are a couple of questions, and I think they are great questions. So I'll try to answer them. So the first thing is like when you express that like hearing people or speaking people may also like touch their face, and sign language, like the answer for that is the sign language detection model just runs if you identify as a signer. So it does not run for speakers in the meeting.
Okay.
Then the second question that you asked is like if you just
right, so it just ignores hearing people.
It ignores hearing people. Yes. The second question that I understood was that like when you back channel more subtle information and the interpreters still speak that out. So I'm not totally sure about that part of the logic, because my team mainly developed this detection models. So we did discuss internally kind of what happens, like this linking of interpreter and signer. Is that kind of like happening also just through the voice detection of the interpreter? And it is possible that it is, but it's also possible that it's not. So I'm not sure kind of like what the state there is really. And you would probably have to try it out. And then,
I will.
And then...
Absolutely will. And sorry, and just as I said, the screen sharing, where what you see is just the voice, so I always end up adding the captions. And of course, my first language isn't English. So what I don't want is the BSL signer disappearing when it's an interpreter disappearing from the screen all the time. And so that's not just voice. I suppose it's saying the other way around, that I have the same issue with Zoom as well, which is that when you've got screen sharing and you've got the interpreter signing, they quite often get pushed off.
Yeah, so I guess you're looking at it from your perspective. I think for the interpreters, like we are not running the sign detection because they're interpreters. I'm not sure like how you can pin them. I think that there are specifics about that. I'm just not aware of them. But like definitely what I can say is from like other participants' perspective, if you present something and you screen share and there's like very little space to show your video, that's exactly kind of the situation where sign language detection comes in very handy and puts you kind of to the front queue of those cameras that are visible. So yes, you will be visible when you share your screen, and that's really nice.
Absolutely. Thank you.
I'm afraid, sorry, we don't have time for any more questions. but please find Oscar in the next break, and I'm sure he'll be happy to answer any more questions for you.
Yeah, definitely.
Again to Oscar.
Of course.
Thank you very much. Just a quick disclaimer.
Sorry. Just sit here. Can I sit here? Are you sitting here? Sorry.
Just to say, unfortunately for the next presentation,
You're sitting here? Oh.
the interpreters haven't seen the slides in advance.
Thank you.
So it will affect the accessibility.